I was thinking, initial thinking was because it is not taught in our university, especially when I did my undergraduate in Bangladesh. It's not taught there. Is maybe you think you have to be somebody like Einstein or somebody like Newton to innovate something. But it's not actually like that. It's actually looking at what you are doing in everyday life and how you can make changes to make it better. Come up with a new system, new product, new process, more efficient way of doing things. A simple thing will be innovative, which is not there, but you are bringing in there to make it better. Okay, so think about this thing all the time. I talk about innovation all the time because we can see innovation, innovative product, and that will only keep the economy going because we are moving away from almost like an agriculture-based society to industrial-based society. Even we are not having industry, large industry in many of the Western countries anymore, and is moving into automation and AI and things like that. So innovation is the key. Okay, and don't think you have to be like a Einstein, as you said, or Newton or something else to become a innovator. You can be innovator if you think what I'm doing today, how I can make changes, okay, to make it better, something new, improve the process. Okay, so let's look at hydro energy devices that have been there for, as I said, 150 years or more. Pelton wheel I talked about. These are the conventional energy source. In a Pelton wheel, you have to have a big reservoir water body here. It comes through a pipe. It has to be very high water body, maybe 100-meter water coming down, coming through a nozzle at a very high speed, and it will impact on this blade, and that will rotate the blade. If you attach a generator on this, you will generate electricity. In order to use that, you need a high water head, maybe 100-meter high. You have to collect water at 100-meter high and get it down through a pipe. That is called Pelton wheel. Then you have a Francis turbine, which can work at less height, maybe 20-meter high water. Advantage of this is that it runs on a what you call a reaction turbine. So these are the water come through this big gap here. Water comes in. This is the body of water, comes through and goes out, and this is start to rotate. So water coming to the blade radially and discharge axially down. Water comes from here, goes radially in and then out. And this is a Francis turbine. Even better this turbine we have is called Kaplan turbine, which works at a even lower head. And that is again very similar system like that, but in this type water flows through the blade axially. So Kaplan turbine, water enters the blade here and comes out, and it makes the blade to rotate around using a technique called reaction force. So this is a very impact, water coming out at a very high speed, impact, and this flows through the blade gradually, is potential energy converted into kinetic energy, put some reaction force on the blade, and that rotate radially in, axially out, and this is axial turbine. Okay, these are the traditional one we talked about, hydro energy. It has got negative reputation. I talked about this already. What is that? It is very big, large, several gigawatts. So that's very good. We generate a lot of electricity at a gigawatt level, but it's very large. That's the challenge. Gigantic artificial water reservoir that you have to create. It disregards social and environmental problem. We talked about this before, right? Social problem, environmental problem. Because you create a gigantic body of water, you flood a lot of area surrounding this dam. People are living there. We buy the land for the people. That's fine. They get the money, but then they are uprooted from the system. That create a lot of social and environmental problems. Thousands of people are forcefully removed from their homes with no compensation to make room for flooded rehab. Okay, no compensation is probably, we're talking about 60 years ago, where we didn't pay compensation. These days you have to pay compensation, things like that. But not many big, gigantic, this type of plant is not built anymore. That's true. In environmental, we talked about, sometimes it destroyed priceless archaeological sites. Okay, and this is an example in Egypt. Okay, they have to remove a whole archaeological site where they have a lot of very old monument, very expensive in a sense, priceless monument in Egypt. And when they put Aswan Dam, they have to remove a whole site from lower part up to a upper part, and they managed to do that accurately. But again, this is not in the correct location anymore; it's in the artificial location now. Okay, and today, fortunately, full consideration of these concerns have become a prerequisite for considering hydro power. These days, you will not be able to do any of these because these days, market of this electricity generation is maybe privatized now, especially in the Western country. These are all privatized system. And if you want to get a permission to build this type of hydroelectric power plant, you need to consider every of these things. What is their social impact, environmental impact. You have to write a report on this impact, details analysis you have to do before you get permission to build those type of power plant. If you have large rated capacity, 50 megawatt or more, we call it a large. Small capacity, 5 to 50 megawatt. Mini rated capacity, 500 kilowatt to 5 megawatt, and micro, the small one, 500 kilowatt or below. Okay, these are the power rating that we do for hydro power plant. So megawatt, we can go up to gigawatt, massive amount. Okay, so that's hydropower, traditional. So let's look at modern, what you can do without going into gigantic type of destroying environment and very expensive, as you say. You have to build a whole dam and civil engineering effort. It takes long month to put it. So hydrokinetic turbine or HKT. How it works? It works similar to wind turbine, and you may have seen wind turbine everywhere in some part of India. Maybe in Gujarat area they have a lot of wind turbine. And which area? Right? Tamil Nadu.
Yes. Lot of wind
Tamil Nadu. Tamil Nadu also, lot of wind turbine there. So the principle is the same. It's a kinetic energy. Kinetic energy means velocity. Velocity coming in, fluid coming in at a high velocity, it impact on a surface or blade, it rotates the blade. So you need to create some sort of rotational motion, basically. So this is the motion of a wind, linear motion coming in. You have to make it a rotational motion with a device, and that device is turbine. Turbine has a blade. Blade will water or air impact on the blade and create some sort of force, and that force make it to rotate. Basically, your linear force, linear velocity turning into rotation. So kinetic energy we are observing. Kinetic energy, not potential energy. Hydroelectric power plant create potential energy. We keep water at a very high level. But here, the flow of water, we attract that by kinetic energy. So, and we can have, that's the key thing. Then we can have next generation of kinetic energy turbine. This could be modular. Modular means you build it by parts, and also it can be very flexible and scalable. You can build it from 1 kilowatt, 2 kilowatt, 5 kilowatt, scaling. It can be deployed in arrays, so you don't need to build a big gigantic turbine. You can have small turbine and build it up in array. Maybe you put 50 of those or 10 of those, depending on how much energy you need. And it serves the needs of residential, commercial, municipal scale consumers. So we are not looking at whole whole state or whole country. We are looking at a small scale, local community, maybe a small village, or maybe 10 houses in a small village, something like that we are looking at. Okay? Importantly, they don't require dams. They don't disturb the water that much. Okay? It disturbs some of the water, but it's not big structure you need in a water body. So they can minimize environmental impact. And so the permission process, if you have to build this type of power plant, the permission process is, regulatory process is easier to get. You don't need to go through detailed assessment you have to go through detailed assessment, but that assessment is easy to do in terms of impact on people, impact on environment, those type of impact, you can easily do the analysis. So this power generation, we can be used as distributed energy source and tied to existing construction structure. If you already have some sort of structure in a river, you can use that. For example, if you have a bridge, many of the river in India, I think you have bridge over those rivers, right? And you can use those bridges as a structure to put in this type of hydrokinetic turbine. You don't need to build up new structure. Okay? Think about mooring system. I asked you to think about in the beginning of my lecture. I give you a task, brainstorm a design. I say blade design, generator and mooring system. How to hold the turbine. Remember that in the beginning I talked about. Now I give you another clue. Bridge.
How is possible?
Huh?
How is possible?
Of course possible. As I say, it depends on your idea, your innovation. You have to justify. Okay? Howrah Bridge, possible, of course. Think about, where you want to put in Howrah Bridge. Of course possible. Yeah? Good. Think about that. I will come. I want a final design answer in the 5th page. Yeah? So initially you may think about, I want to moor it like this. But when I talk about bridge, you may think, okay, let's put it on a bridge. Yeah. Or you may think about something else also. Yeah, it's not necessarily bridge. I give you just one idea, right? You have to think about. Okay. Another idea, maybe put it on a boat. Expensive to make, or maybe very expensive to make country boat. You can put your turbine and use that country boat as a structure for your generator, everything on a boat. Yeah, so that's possible. And so you can. wrong answer. Whatever you market, if the people say or the businessmen say, okay, I want to invest in your idea, let's build a with you don't need to convince me, you have to convince the businessman, market. Yeah, everything is possible. I talked about innovation all the time, that we try to teach our students to think that way, because traditional engineering, I get a good job, and then I work in a good job, I get a promotion slowly. That was the traditional way of job, but it becoming rather difficult. Okay, so many of our engineers are now become like an innovator. But as I said, innovator means you don't need to be Einstein or Newton, right? These are two names I say, but maybe I can say other name also. Okay, it's all about you think about how you can make life better. What are the challenges I am facing in my daily life, and think about how I can make changes. That is the innovation. Okay, so sorry to digress, but that's the whole idea. Okay, okay. What is the advantage of this type of turbine, hydrokinetic turbine? Is flexible and intermittent. Intermittent source, you have to think about, as I say, water flow rate is almost uniform in many of the rivers. Okay, you have to think about how much water varied with time and with space and things like that, but it's more or less sometimes intermittent, sometimes continuous. Easiest to regulate by storage. So if you have a lot of flexibility or intermittency, you just put a battery to storage energy basically. This resource is widely dispersed. You can see the river is everywhere. I saw you the map of India, right? Many rivers there, and they are high flowing river. And I give you 6 locations, but I can give you 50 locations actually, more than 50, or maybe thousands locations where you can put this type of turbine, okay, and make it useful. And these are small structure. So you see, maybe you have a big dam, and your enemy country thinking, okay, we'll create some bad thing for you, so they can come and bomb this dam, right? And that will flood the whole city, town. Lot of disasters can happen. But if you have this type of distribution, small wind turbine, water turbine, hydrokinetic turbine in different places in the river, then you are not disturbed by the war or civil disturbance where you can create big problem there. Okay? Okay, so that's the whole idea. Now let's look at some of these why you are becoming interested in hydrokinetic turbine. Scientists are becoming interested in hydrokinetic turbine. Okay? They are attracted attention of researcher because minimal environmental impact. These are the things. Minimum environmental impact compared to big dam-based things. It's small. You can serve to remote off-grid communities. And when you have a remote off-grid community, they only have diesel turbine, diesel engine to generate electricity. And some remote places, you have to supply diesel because diesel is not produced there. You have to bring diesel there to serve those local communities. So this is an area, I think, in, let me look carefully, this is an area in figure shows a river in Colombia, in South America. These are very remote location here. Small community here, and to supply diesel is very difficult. Okay, traditionally is supported by diesel but as you say, it's very difficult. But they have a nice free-flowing river. I will give you an example of this later down the line. But a nice free-flowing river here, and then you can put turbine, serve these communities. These are the places where solar is not very useful, wind is not very useful either. Only options you have water flowing through. So if you can use those, that will be great. Okay. So before I go to next slide, I will now ask one or two questions here. And I asked you to come up with a design. Have you thought about any of the design of the turbine? Turbine, how it can be? Did you make any sketches of the turbine? Anybody? How can this turbine look like? Axial flow, radial flow, or vertical axis, horizontal axis? Anybody thought about any turbine till now? Anyone?
Velocity diagram.
Huh?
The velocity diagram.
You did velocity diagram of the turbine.
Sir, I have studied about it.
Okay, so what type of turbine blade you thinking? If I tell you, okay, design me a hydrokinetic turbine,
Basically, I have made impulse turbine.
you okay, impulse turbine. We are not doing impulse because it's a kinetic energy. It's not a Pelton wheel. Pelton wheel is the classic impulse turbine, right? You can do the velocity diagram there, but for hydrokinetic turbine, what type of design is more suitable?
So we can use the vertical axis turbine.
Vertical axis turbine. Why?
Or like a hybrid turbine. The proper intermediate of the vertical axis turbine, like the subordinates and direct, mixture of the subordinates and direct.
Okay. Anyone else? Thought about any other design? Okay. So let's look at one or two design. But again, I say you come up with your own idea. Okay. So these are the design. There are many other type of design. I only got this type of thing because of the copyright issues, right? I can Google search and cut and paste any of those figure, but I am not allowed to use that for giving a talk like this. I have to have copyright. So only thing I found it on those who are open access or have the permission to use. Those are the thing I am showing you here. So most of the hydrokinetic turbine are axial flow, something like that. 3 blade, a hub is connected with maybe a monopile connected from a single structure monopile. Okay. These are the most type of axial flow turbine. Okay. So 3 blade here. This blade can have very thick at the root because you have to have very strong to rigid to withstand water flow. Water density is 1000 times more than air density. So wind turbine blade is exposed to the less dense flow, but obviously velocity is higher in wind turbine. But here, water is coming and hitting this blade. So you need a shorter length, not like wind turbine. Wind turbine length is very, very long, maybe 100 meter, 150 meter long wind turbine blade. Here the blade size may be 0.5 meter or 1 meter, something like that. It has to be thick here, and to get the maximum power output is twisted here. So that gives you the maximum power output and things like that. Uniform uniform torque over the blade kind of thing. This is one type of design, axial flow. However, your friend says vertical axis turbine, right? Yes. Did I hear you correctly?
Yes.
Yeah, vertical flow turbine. So this is a vertical flow turbine with 1, 2, 3, 4 blade. You can have a 3 blade also. You can have 4 blade, 5 blade maybe. So you look at the blade here. Blade here, 1, 2, 3, 4. It's connected to a central shaft using those connector pipe. And when the flow comes in, it hit it here, and then it will start to rotate. What is the advantage? Can anybody tell me what is the advantage of this type of turbine? You said Darius. Remember the name. Darius turbine. Vertical axis. What's the advantage of this? If you look at the wind turbine, we usually see this type of turbine. Okay, so what is the advantage of this type of turbine? Anybody can think of, tell me.
So drag is less and lift is more.
Drag is left, lift is more. Yeah, good idea. So lift more means
More
more
power.
more power you are getting. Yeah, lift force is high on this blade. Yeah, compared to this, he is saying. I am not saying. Your friend is saying. So this one compared to this one, where the force acting, he said the lift is more here, drag is less. You get more power for the same velocity, right? For the same velocity, if it is 2 meters per second, you get a better lift here. Okay. What's the other advantage?
Economical.
Economical. Why?
Because if you take the example of the current picture, what we have shown over here, the straight blade turbine is basically the manufacturing cost is very less as compared to the symmetrical blades. So
What you said is there, but in this blade is straight blade, so is cheaper.
RPM, sir.
RPM good. What is the RPM?
Actually, in revolution per minute, it will be more here because the blade is not that much sound.
Is not submerged in water. Okay. So what happens is that you have a blade design here. Just behind the blade, you have a generator, which is sometimes directly coupled, sometimes is coupled with loss, mechanical loss. But here, directly coupled. This is your electrical generator out of water. Because of out of water is a easy maintenance. It doesn't need the kind of a water sealing that you need, and so it can be cheaper and easy maintenance. Get access to it. You can have the power line from there into the shore many different way, either submerged or overhead, whatever way you want to do it. Okay, now we go back to mooring system. We talked about which bridge you talked about? Hooghly Bridge. Oh, sorry, Howrah Bridge. Howrah Bridge. Is there a Hooghly Bridge also, or I just made it up? Huh? Oh, Howrah Bridge and Hooghly River. Okay. So here the mooring system. What do you think? What type of mooring system is there? How it is put in water? So this figure, if it is not clear, it looks like to have two float, right? Two float, or maybe say you can say similar to two boat, a country boat. You can create this type of float here, and then structure over here, fan, your turbine blade rotating, hanging from this what do you call boat, and so you are generating electricity here, right? So you don't need the bridge. You can have another type of float to keep it here. Okay. This, look at the blade. Is a straight blade. Here is a straight blade. Okay. Now, what happens? So water is coming in. It hit there. You get a high lift. You say it starts to rotate. Then what will happen? There is a gap here where no blade is facing. water. The blade is rotating, right? So it creates a kind of a non-uniform torque on the shaft, not uniform. So it's more power, less power, more power, less power. So you have to probably balance it with some sorts of control mechanism or things like that. So how can you distribute torque uniformly on this blade? Okay. You understand what I'm saying? Water coming in is hitting there, it starts to rotate. So when you are facing like this, water coming, hit here, it moves away. So another blade here, then moving like this, then blade will face. So in between, the water hitting this and that. So basically, the force or the torque on the shaft is not uniform in this type of structure. Because it's not all the blade is facing flow all the time. Here in this, all the blade is facing flow all the time because it's rotating axially, flow is coming from the front. But in this type, it's rotating like this. So all the flow hitting this blade, not all the blade is exposed to flow all the time. Okay, there is a gap where flow is going through. So the torque is not uniform on this blade. So how can you make torque uniform? How can you make torque uniform? That means all the blade is in touch of water. When the water is flowing, some portion of the blade is facing water. How do you do that? Your friend said before. Did you say that before? No. What you do, we change the blade structure, make it curved. Have you seen that type of blade? This type of blade makes it torque is now uniform. Yeah, because this front part of the blade is facing water, is rotating away. Then this part is facing water, then this part is facing water. Once it's rotating, every part of the blade is in contact with water. So that's the advantage of this type of twisted blade, where you get more uniform power on the shaft. So you can don't have the micro changes in the power output, right? You need to have a uniform rotation of the blade. That's more important. So uniform torque distribution by twisting the blade. Yeah. Okay, another type of advantage of this type of blade is this type of blade you can put it horizontally as well as vertically. That's a good design. In a sense, this you can put it horizontally as well as vertically. This is your vertical design, that's fine. But you can have this one 2, 3, 4 along the river width. This type of design, you can put it, turn it around. Think about turn it around 1, 2, 3, 4 along the river. You can put it. Okay, and so that's it. Good. Okay, let's look at economics. I talked about economics before, right? So because you can come up with a design, very fancy blade, fancy turbine, nobody will buy it. Nobody will install it. Why? It will become expensive. So we need to come up with some sort of economic aspect. So cost of the turbine itself is small, but turbine itself is small. Cost, this blade. Then you need other things. We need gearing system, we need generator, we need mounting structure, anchoring, electrical cabling, and converter, inverter, and things like that. So, price goes up. This blade, as I said, this is only a small part of the cost. But as a mechanical engineer, we actually love this part. We can do, have you heard about computational fluid dynamics or CFD? What you do, we create the design, we put it in a computer and we run a simulation, we can see what type of flow happening, and these are quite fun, quite interesting thing, and it gives you very nice interest on the subject area. Okay, and you play with this computational fluid dynamics for whatever you like to do. Okay, and then you forget that is the economy that is important, and this part is only a small part of the whole thing. Whole thing include gearing, generator, mounting structure. I come back to Hooghly River, right? Howrah Bridge.
Yes.
Okay, or boat, or whatever, mounting. Very important. Anchoring. If you create a boat like that, and then you keep it in water, what will happen? It will move away. So you need to have anchor. And this is the anchor, I think. This straight pipe going down, anchoring it. Or you can have simple anchoring with a cable or thread, whatever you call it, with a anchor to fix a boat there, right? Anchoring system. Electrical cable, and then electrical control, converter, inverter, all of things. So our objective is to remember, first challenge I give you. I am not forgetting that. You have to keep in your mind, I will need answer. A design from you after 5 days. We want to design a 5 kilowatt water turbine running at 2 meter per second. Here it's 3 meter per second, but we saw 2 meter per second. It costs tens of thousands of US$ for supply only, not installation, making the install cost prohibitively for all but on of demonstration. So usually when you come up with the technology, you can apply for funding from the government sources or European Union or other funding body. Once you get the money, you can build this type of thing and demonstrate that it works. And that demonstration costs a lot of money. It doesn't matter because first innovation, you need to show it works. And in order to show it works, government usually pay the money to build a demonstration unit. And whatever cost is there, it doesn't matter. But when you want to commercialize it, your electricity cost, what you call levelized cost of electricity. Okay, we'll talk about that. It takes into account capex and opex. Capex means capital expenditure, opex means operational expenditure and things like that. From there, and how many years it will last? Maybe 25 years usually, or 50 years, depending on how long it will last. We can calculate levelized cost of electricity. And that electricity price has to be less than what is available now in the market. Otherwise, nobody will buy it at the end of the day. Okay? So, as an engineer, you need to be able to calculate localized, levelized cost of electricity produced from this system. And we'll look at how we can calculate that further down. Okay? But it is the economics that will either kill your innovation or you can become a millionaire or billionaire. Okay? So, what is the future prospect of this? We need a simple, reliable, affordable turbines. Turbine, affordable. Okay, turbine, everything you have to think about, can I cost? If you have a 4-blade, if material cost is high, 3-blade, material cost is less. But that you have to balance against power output or the uniformity of torque. And then think about manufacturing. Manufacturing 4-blade may be easier than 3-blade because of 4-blade is easy, just for 3 you have to accurately measure the angle while you are putting this 3-blade. Okay, so simple, reliable, affordable turbines we need. We need a huge profitable potential market for such turbine to deliver an useful power. So there is a huge and profitable potential market there. There. You come up with a new design, cheaper, simple, reliable, market is there to buy the innovation from you. And there are thousands of sites in many moderate sized river around the world. Thousands of sites you can put it. Okay. Now I have two questions here. I will give you a break of 5 minutes, then move on to the next topic. Before I go there, you remember the figure I showed you about my first lecture, right? Introductory lecture. If I can go back to there, I give you a 5 minute break, as you said, and then move on to the other topic. That's how we'll start in a minute. Yeah, looking at this river here, looking at this figure here, this is our university. I told you, river here. What is the potential of putting a hydrokinetic turbine in this location? Looking at the figure, you tell me what is the potential of putting a hydrokinetic turbine in this river next to our university here. What do you think? Should I put a hydrokinetic turbine here? Looking at this figure, nothing else. You make your judgment looking at this figure. Yeah? As I say, it has to be not right or wrong. It's just a guess answer, fun answer. Anyone? You want to say something?
So I think there is not much more potential in that water because water is still over there.
Okay.
I think so.
Okay, you think so. Okay, that's a good answer. Another one, though those who haven't contributed yet, what do you think? Answer? Yeah, you
So turbulent flow is important to produce hydropower.
yeah, velocity is important. 2 meters per second they're talking about. Yeah, usually it will be turbulent flow. Yeah.
We can generate a small amount of mass.
Small amount. How small?
But the velocity of
Yeah, it is actually very still. Okay, water velocity is almost zero many of the days, and many of the days is maybe 5 meters per second. Why is that? Because upstream we have a mountain where a lot of snow. So when the snow melt, ice melt, you get water coming down very high speed. Maybe 6, 7 meter, 8 meter is uncontrollable water. And most of the water depth, here water depth, we can cross walking. If you want, maybe water to up to your knee. Water depth is not that high either. Okay, you can just across. So we did lot of analysis here, and we found out it's not possible unless you do some type of canal, maybe some source of potential energy difference you create upstream, downstream, kind of a dig here inside, dig a canal, make it up and down, then get water through the canal, or kind of a, have you heard about vortex turbine? Take a canal through and then rotate it. So unless you do some sorts of additional work, because this side we call it a energy park. We try to do a lot of renewable energy research here, but hydrokinetic is the one we could not. After doing a lot of calculation, we found it's not possible. Yeah. Okay, so I'll give you a maybe 5-minute break. Okay. Okay, so let's make it start. Uh, so we look at different type of turbine. Now we'll move on to engineering part of the work. Okay. So how can we design a rotor of a horizontal axis hydrokinetic turbine? Then we'll talk about vertical turbine also. Okay, so we start off with horizontal axis turbine. So what is the principle? Principle is actually start off with this formula, which is called maybe calculation of power. Look at it here. This is the power output you are looking for, 5 kilowatt I talked about. Half. Rho is the density of water, which is 1000 kg per meter cube. But there is a little bit of point here about the density. You remember that in the introduction, Professor Somnath Chattopadhyay, he talked about water with silt, okay, water mixed with some mud. Okay, so if you have this type of water, your density maybe changes and maybe a little bit higher. Okay, so density, be careful about what type of density you're using, what type of water with it mixed with some other solid particle or not. This is density. Area is the swept area or the cross-sectional area of the turbine, and this is calculated as pi over 4 diameter square. Then you have a velocity, water velocity to the power 3 times a power coefficient, we call it Cp, and then efficiency. This efficiency is about 70%. This efficiency is efficiency between motor, rotor and generator and things like that. So if your output is 5 kilowatt electrical output, your mechanical output has to be more than 5 kilowatt to get your 5 kilowatt of electricity. Okay. When we rate any turbine as a kilowatt, that is actually the electrical power you are getting. So you have to have a efficiency that take into account conversion of mechanical energy into electrical energy, and that is 70%, just an approximate value. That Cp value is base limit. We asked you in the beginning, what does it mean? It means what is the maximum efficiency you can get or from a turbine, and that is 0.593. From the theory, we can prove that this is the maximum efficiency that you can get in a turbine. This is what we call aerodynamic or hydrodynamic efficiency. Aerodynamic or hydrodynamic efficiency. Remember that. This is the limit. But we usually don't get that. We usually get 0.4, 0.35, this type of number. Okay, so from here, this is the easiest way. If you know this formula, if I ask you to design a turbine, 5 kilowatt, your velocity is 2 meters per second. From there, you should be able to calculate swept area, and from there you calculate your diameter. That's the first step. How big the turbine will be. Okay, that's the first step of calculation. R, radius, how big. Then you calculate other parameter slowly. Okay, so when I say design of a turbine, very simple, rough calculation is diameter. Is that clear? And then radius. Then you can calculate length of the blade. So what is this formula coming from actually, and what is that Cp? So first of all, I am talking about a actuator disk theory that will help you to get value of Cp, power coefficient. That's a very important parameter. And why it is a base limit, why we cannot get more efficiency than 0.593 or 59%. Why is that? Okay, so let's look at a very simple theory called actuator disk theory. So think about this is your turbine blade here, turbine here. The flow coming at a density of rho infinity and u subscript infinity. This is the key parameter, u. This is the free stream velocity. It is not disturbed by turbine, free stream velocity. It is far away from the turbine, it is not disturbed by anything. Okay, that is the 2 meter we are talking about all the time, 2 meter per second. Okay, when it comes here, near the blade, what will happen? It will change little bit by the blade. Before entering the blade, it was uniform, nice. Before entering the blade, it drops little bit here. Then, through the blade, it comes downstream section, it starts to come down here. So this is small change happening due to what we call induction parameter A, and that is the important parameter. So that we can think about the blockage effect or something like that. So because of this turbine blade rotating, this free stream velocity changes little bit before it enters the blade, and that is how much is disturbed by, we call it this A, or the induction velocity. Okay, just remember that. And A is a critical parameter from that theory. If you look at the pressure profile, this is your pressure upstream is uniform. Just before the turbine blade, pressure is start to go up and then drop through the blade because the energy is taken over from the, and then the pressure is start to go up and become uniform pressure again. Is a, what do you call it? A pressure recovery. So before the pressure, after the pressure is the same. In between here, there is a change of pressure profile, a discontinuity. Pressure come up, goes up, comes down through the blade, and then after the blade is low, it has to recover back here. And the velocity continuously drops. And just before entering the blade, it has changed to U1, we call it a U1, which is from infinity times 1 minus A. A is the induction parameter. That's the important parameter. How much velocity is changes due to the blade. And from there you can calculate power, torque. We are not going into any of these equations in detail. What you can say that equation you can write, first of all you can write equation for power, equation for torque, then Cp is power coefficient. Okay, sometimes we call it efficiency, basically power coefficient, which is the power is generated by half rho upstream power, basically. This is the upstream power. This is the power hold in the wing, but we cannot extract all of the power. Some of the power we are extracting. Why? There is some induction happening here and some pressure recovery happening here. Pressure goes up, comes down, and then recover back again. So that recovery process doesn't allow you to extract 100% of the power. If you want to extract 100% of the power, pressure has to go down. But pressure doesn't go down, it recovers back again to whatever the free stream pressure. That's why that recovery process, because of the recovery process, you don't get to extract 100% of the power that is available in the flow. So available power in the flow is half rho free stream velocity to the power 3 area times here, right? And this is the power you are extracting, and that power extracting include this A, induction. And you can apply continuity and momentum equation. I am not going into details of that. I am just giving you the physics of the flow, so you can understand physically what is happening. You cannot extract 100% power out from the flowing fluid. That's the key thing. You cannot extract 100% power output from the flowing fluid, because you have to have pressure recovery. Pressure has to come back to its original value. Okay, you cannot have a vacuum system. Flow is temporarily disturbed near the turbine, but then pressure has to recover. And to recover the pressure, velocity has to come down continuously to the blade, and then a discharge velocity, which is low. Okay, from there, this calculate the pressure coefficient in terms of A, induction velocity, and you want to extract maximum value here. To get a maximum value, you have to differentiate with respect to A, and then you write is equal to 0, and that gives you the value of A is 1/3, and Cp is 16/27, which is 0.569. So that's the logic. You are extracting maximum value of Cp. To get the maximum Cp, your A has to be 1/3, and putting 1/3 back into here, you get a maximum Cp of 16/27. So that's the maximum you get. You have that's the law of physics. You cannot destroy the law of physics. That's what it is. Okay, in the turbine. Okay, this has been running for a long time. That's right. Yeah. Okay. Is that clear? So that is all we call actuator disk theory. This is a very simple theory, and you can use that theory to design our turbine again. Okay, so that's basically is to find out your power output. This time I have done another calculation. Your power output is 746 watt, but our objective was 5 kilowatt. I didn't do the calculation because I want you to do the calculation, so that's why I didn't do the 5 kilowatt power calculation. So you have 746 watt of power generated, and water velocity is 1.5 meter per second. You have a Cp value of 0.4382. As I told you, this is the maximum theoretical value, which is 0.593. Theory it says, but in practice, different turbine produces different value of Cp. It is okay, 0.4382. Okay, that's the Cp value you get. Your efficiency is 70%. Your density of water is 997 kg per meter cube. If you put this number into this simple equation I showed you here, this is the Dijen equation. You put it here, you get a value of area, swept area. From there you can calculate diameter and also radius. So your radius now coming into 0.678 meter or 0.68 meters. Okay, so that's the blade radius. If you assume there is no no hub, so there is a hub radius. So we can take into account the hub radius. We can reduce the blade size further down. But actually, this is the total length from the center to the tip of the blade. Okay, and we can, as I said, use the simple formula to determine how much length of the blade we need. What type of blade we need, we'll come to that in a minute, but this actuator disk theory at least tell you how big the size should be. Okay, now if you have to take what type of blade we need, now we have to go into details. So let's look at aerodynamic details. Okay, before we do that, okay, say, there is exercise. Understand the river characteristic. That is how we can use this actuator disk theory for designing a turbine. Okay, so you first of all you have to understand the river characteristic. Measure the average flow velocity of the river. That's the important. For Indian rivers, this typically ranges from 1 meter to 3 meter per second. So in India, velocity is 1 meter to 3 meters per second. That's a very good quantity of velocity. Depth and width of the river is also important. You need to know that. But in Indian river, these are very deep and very wide. So that's not a problem either. Okay? And so you can use the disk theory to calculate diameter, as you say, from that formula. And so this is your formula again. If you know your CP value, you can calculate swept area and diameter. Another thing you have to think about is tip speed ratio. That's an important parameter, which is speed of the tip of the blade divided by speed of water. Tip speed ratio, and this value is taken usually 4, 5, depending on the blade type design. Tip speed ratio, if you plot tip speed ratio versus efficiency or tip speed ratio versus CP, you can find that different type of turbine has a range of tip speed ratio to give you the optimum value of CP. Some of the turbine blade has got very narrow CP value, and some of them is very wide CP value. Okay. So what is talking about CP? So there is the value of tip speed ratio here and CP value. So if you take this curve here, your tip speed ratio, optimum tip speed ratio is 6. If you take this curve here, your optimum tip speed ratio is 4. If you take this curve, is again 6. So tip speed ratio for each type of blade, a particular tip speed ratio gives you the maximum CP value. And that again depends on the angle of attack. I will come to the angle of attack in a minute. So this parameter is again a very important parameter. This is after effect. That means you have done a lot of experiment with the angular attack of 0, 5, 10, 15, and then you plot the graph. It looks like that. Now you are given this knowledge. If I give you this knowledge and tell you what is the tip speed ratio you need to get the highest CP value, okay? So to get the highest CP value, what is the tip speed ratio you need? So a turbine only works at a particular tip speed ratio. Okay, if you don't set up this and tip speed ratio, then give you the what is the RPM you need, what is the RPM you need to turn the blade to give you the maximum efficiency. Because once you fix a tip speed ratio, this is your water velocity and this is your diameter of your radius of your blade. From there you can calculate rotational speed omega. Calculate rotational speed. So tip speed ratio you have to decide yourself as a design parameter. How you decide yourself what tip speed ratio you need? Do you take tip speed ratio of say 16 or tip speed ratio of 14? No, because that gives you the 0 CP value or very low CFP value. Tip speed ratio between 4 and 8 may be good. So that gives you the maximum value of power coefficient CP. And there are a lot of curves generated like this for different type of turbine. Okay, so that information is already there. Other scientists, other engineer, other researcher has created this type of graph for you. So when I ask you to design a turbine, you can calculate radius and then you can decide on what is the tip speed ratio you need. From the tip speed ratio, you can calculate RPM, what is the rotational speed of the turbine blade you want. And that has to be synchronized with the speed of generator. Because otherwise, generator runs at a fixed speed. So either you have to have a gearing mechanism or something to control that speed again. Okay. So actuated this theory, a very simple equation which are there that will actually help you to do kind of a design to start off with. This simple equation helps you to start off with the design process. Now what type of blade we did? You can go back and look at more complex theory. So let's look at complex theory. Let's look at complex theory here. What you call blade element model. Blade element model. And so we'll spend a little bit of time here to make you understand what is happening. So this is your blade, 3-bladed axial flow turbine, 3-bladed axial flow turbine. Okay, three-bladed axial flow turbine. So if you think about this is rotating this way at a speed of omega, total radius from this center up to this point in R. We take a small element dr through the blade, this area here, and then we can do force balance and things like that, calculate force, calculate torque, and then integrate over the whole radius to give you what is the value of torque, and from there what is the value of power that is generated, and this is the omega, that is the rotational speed fixed, and we can calculate force, different forces acting on this element. Okay, so a small portion we are taking out of the blade. So this is the your whole blade length. We are taking a small section like this. Dr is very small. In a figure it looks like very big, but it's a dr, small length along the length of the blade. You see this radius is very high. This at the tip, the blade size is small. This blade size is high. We define the blade size by a parameter called chord length. Chord length simply the length between tip and the end point here. The chord length C. If you see that this here, a chord length is drawn here, dot dot from the tip to bottom point here, end point here. This is the chord here. And you see the chord length is high at the rotor half, and it starts to drop, and it's very small here. Okay. Now the important part is to understand this triangle here. And one of your friend already said he did some analysis of this triangle. Who said that in the beginning? Somebody said that. That he did a triangle. You said that, right?
It's a velocity triangle.
Velocity triangle, yeah, something like that. This is also a velocity triangle. You are familiar with that. So let's look at this tip here. At the tip, what is happening? At this tip, blade is rotating. So we think the blade, this is the angle of plane of blade rotation. This way, and air is coming this way. Air is coming from the bottom. Air is coming from the bottom, is rotating this way. Rotational blade rotating like this. So at this tip point, there are two velocities you can see. One is air coming in this direction, and then is rotating that way. So that's the key thing. First of all, you just draw these two arrows. Air direction, rotational direction. Then you take a end point here to end point there, add it. So this is your actual flow direction that your blade can see. Okay, the flow is coming this way, blade is rotating that way. So if you take the velocity vector of these two and take a resultant velocity, relative velocity you call it. So from this point to that point is the relative velocity, and this is the velocity, and this direction the blade is seeing the air or water coming and hitting the blade. This direction, relative velocity direction. Okay, and this is your complete triangle. So we have a velocity going this way, a velocity going this way, and then this is our relative velocity VR. And that is the important parameter. It can be calculated from this and this. And then all the angle is happening here. So first of all, angle is the phi angle. The angle between relative velocity and the horizontal plane is a phi angle. We can calculate that by knowing these two velocities. But these two velocities we cannot know beforehand, because though we know the velocity v1, which is free stream velocity, but there is a parameter called A, which is induction velocity. The amount of velocity drop due to blockage of the blade and things like that, blade is rotating. Again, similarly, omega r is the rotational velocity, but that is changed by A prime here, 1 plus A prime. And A prime indicate the flow is going through the air or water behind the blade is start to rotate, the vortex created, and that vortex influence the angular velocity. So axial velocity coming from air or water, that is influenced or changed by induction parameter factor A. Similarly, your rotational velocity also impacted by velocity A prime. These two parameters you have to find out later down. Then you can have a chord length, chord direction. The angle between relative velocity and the chord, we call it a angle of attack. That is an important parameter, because any aerofoil, a angle of attack determine how much is the lift force and how much is the drag force. Usually our angle of attack is 5 degree to 7 degree. You fix it, okay? That gives you the optimum angle lift force. So now we can calculate, by knowing this triangle, we know the direction of lift force and drag force. The drag force will be along the relative velocity direction, because that's the direction of the flow coming. So drag is along the length here, same direction. Perpendicular to the drag is the lift force. And we know lift and drag combine together to give you the rotational flow direction, the force into useless force, lost force, that is a reactive force or normal force we call it, and then the flow force, that is this force here, this direction or opposite to that, this direction, that make blade to rotate. We want to find out the force that make blade to rotate, and this is this one. Some portion of drag, some portion of lift, and some function of sine F. F is the function here, right? So you start off with a triangle, very important triangle, and then we calculate different angle and things like that. So, and the direction of drag, direction of lift, and from the direction of drag and lift, we can take a component normal, and we can take a component along the rotational direction. So here the starting point is these two velocity, this and this. This is your air velocity, V air, maybe, and this is your rotational speed. I didn't put A here. And then your relative velocity here, VR. Then you have to measure this angle. So VR direction is the drag force, and 90 to the VR is your lift force. That lift force doesn't rotate the blade because some component of the lift. So we have to take a component of force in that direction that give you the lift, and some component of the force in upward direction that give you the normal force. So lift force and drag force then again converted into this type of tangential force and this normal force. So your starting point again is the two velocity, which is air velocity and rotational velocity. Then you calculate VR. Along the VR is your drag force, perpendicular to VR is your lift force. Once you get these two forces together, you then take another component to give you the force in the rotational direction and perpendicular direction. So a lot of algebraic calculation along blade angle to find out what is your angle of attack. Angle of attack is fixed. What is that? To get that angle of attack phi, how much you need to have this phi angle, and if you know the phi angle, how much blade you then need to twist to keep same type of uniform distribution of torque along the length of the blade. So you don't need to twist the blade, You can have a flat blade that give you less power. You really need to optimize and extract the maximum amount of power. Every step you have to twist the blade. Every location you have to twist the blade. Okay, so these are the set of formula to model this turbine using blade element method. Phi is the relative velocity that is coming from your knowing air velocity and what is the rotational velocity you need. Rotational velocity again depends on air velocity because you fixed your lambda curve. You fixed your lambda curve. Lambda is your what do you call? Ratio. Yeah? So tip speed ratio. Tip speed ratio. Lambda r is the speed ratio at different locations. Tip speed ratio at different locations. So from tan phi, this area, this induction parameter is a problem. Okay, we don't know the number to beforehand. We have to calculate it iteratively. There is iterative process. Tip speed ratio is given by this formula at different r. Relative velocity we can calculate from this equation here. These are simple algebraic equation. Then is a force component, normal direction and direction of the torque. This is very important parameter that give you the tangential force, rotational force, that give you the torque and things like that. And Cp value is this optimum value, then you can calculate. Okay. So this is the formula that allow you to calculate a twist angle. Okay, so you will be given again power. From there you calculate the radius. Then you select a aerofoil. You can name a aerofoil NACA 0012 or NACA 0018 or 0015. Take any blade. That has got an optimum angle of attack. Take an optimum angle of attack of 7, suppose. Then your objective is to calculate twist angle for different radius. And that twist angle will then give you the optimum power. However, we don't know the value of A and A, so we cannot calculate twist angle because you cannot calculate phi. So you have to assume a value of A and A prime, calculate it, update the value of A prime, and do the whole loop of cycle over again until you get a uniform value of angle of attack at every section. Okay, so to do that, you need to have a simple iterative process. Okay, so let's make it a little bit of easier calculation, not getting 100% efficiency. So let's make the calculation a little bit of easier. So for each, we start. This is our half. This is our tip. We need to know for each R, we need to know Cp. So this is another R, another C, another R, another C, another R, another. For each of these R, you need chord length. You see the blade way is designed here. The chord length at the beginning is high because this part has a less angular velocity here. Omega R is less because the radius is small, omega R is less. So you have to have a bigger area to extract more, equal amount of power from the whole of the blade. So this is a thicker blade here, not thicker, longer chord length here, longer chord length here, and as you move away, longer chord length here, as you move away, the chord length becomes smaller. So R has an impact on chord length. So this is the equation for chord length. For 8 pi R sine phi divided by 3 B CL omega. B is the number of blade. Again you predetermine the number of blade. How many number of blade you play with? maybe 3, maybe 4. Okay, so from there you can calculate your C here. Then you can calculate A from this formula, A star from this formula. Phi is 2/3 of tan inverse 1 by lambda r, and this is the what you call solidity of the blade, which is number of blade coordinate divided by pi r. So you can use that simple formula to design the blade. Once you design it, power curve, one thing you have to remember, when you are talking about 2 meter per second, this is your 2 meter per second, that gives you the rated power. But your flow can be less than 2 meter per second or more than 2 meter per second. If the flow velocity is more than 2 meter per second, you don't try to attract more power. You just attract the your rated power, okay? Otherwise your system will break down. You cannot control the whole system where you are supplying power. You have to have a rated power, you control at that. So if your velocity is more than your design velocity, you don't basically extract more power. Similarly, if the velocity is less than your rated velocity, then you can extract some power, but it's not at a highest efficiency. If you want to take a highest efficiency and things like that, you have to do a little bit of controlling. That will come later. So maybe this is 1 meter per second, you start producing power, and then after 2 meter per second, you reach a maximum, your rated condition. After that, you don't generate more power, whatever the velocity is. So this is the cutting speed, the speed at which you start to generate power, and then this is the cutoff speed after going up. You don't change the velocity, you don't extract more power by changing the blade angle or things like that, you control it. Okay, so let's look at vertical axis turbine. This is horizontal axis, simple calculation. Vertical axis little bit of difficult. What we are looking at is two blade. Flow is coming from left to right. This is the blade. Once the flow passes the blade, what will happen? Before it reaches the next blade, your free stream velocity is already changed. So if this velocity is 2 meter per second, it comes, hit the first blade, then it comes out, then the velocity here may be 1 point per meter, because the flow is already disturbed by this blade. So what is the amount of disturbance? I don't know, we have to calculate. And that lower velocity flow then strike this blade and create little bit of again drag lift, whatever it is. Okay, so you have to consider 2 blade down. Previously, we just considered 1 blade at a time, and then transfer it to 3 blade or may not. But here, you have to consider 2 blade at the same time. So we have a 2 actuated disc, one flow coming in through the blade, and then become little bit small, come through the next blade, and then going out. That's the 2 actuated disc now. 1, 2, 1, 2. 1 blade, 1 actuated disc. Okay, so you can then exactly the same principle that we looked at. You have your blade here. You apply your velocity of flow coming in, and rotational direction velocity is omega r, and both of them resultant force give you VR, and the angle between them is phi. Alpha here, what is the form? Phi previously. So once you draw this one, you can then play with different type of velocity changes. So you can then come up with an equation for upstream velocity. We can come up with a equation for downstream velocity. You can come up with an angle of attack, this one at upstream, and angle of attack when one of the blade is downstream somewhere here. So by using the same logic, same velocity vector kind of thing and velocity triangle, we can then apply the same principle in forward and backward blade. and come up with few equations. So at the end is a simple algebraic equation that I am not going to go through, but at the end you should be able to calculate force normal direction, which is useless, but tangential direction will make blade to flow. So it's a very simple equation, half rho CL velocity square and Cp at the top. So finding this CL and Cp, these are the challenges, but those equations are given here. So for this type of radius axis turbine, your design process changes, okay, little bit. So this is the design flow chart. Initial parameter we know is the RPM, is the velocity, radius, and few other parameters given there. Induction factor we don't know. That's the main thing. Induction factor don't know. So you have to assume a value of A and assume a value of A prime. Then you go into the equation. You select a blade, get CL and CD, and then see how the value of A changing depending on the situation, and you either accept a value or you can say the A value is not matching, so you go back and do the calculation first and repeat it. Finally, when you get the A value, you put it in the equation for power coefficient and things like that. So this is much more complex calculation compared to the previous calculation. Okay, so all type of equation I have, then you can put it in a software to come up with a quickly a design parameter. Okay, so the software is written in Python. Anybody knows Python here? Python code? Only one. Anyone else? Okay, two. It's very simple. Anybody knows MATLAB? MATLAB, okay. So I have got two code actually to show you. One is written in Python and one is written on Excel to design a blade. So I will share the code with you, so then you can design it at your own time. Okay. So let's look at how the blade works. So if I can show you here, give me a second. This is your Python. Let me see if I can find the Python code. Okay. Python code runs on a software called Spider. Spider.
So you can also run with the Google Colab as well.
Oh yeah, exactly. Yes. Google Colab. Okay, so this is the code I have. It's very simple. Even if you don't know, you can read it and learn. So if I run it here, so what I have got? First of all, I have put all those equations into simple form. So first of all, you need to find out chord length. So if you go back to, okay, yeah, I have to go back to. No. Okay, let me get if I can get strings here, right? Okay, then go to teams. Which one is the teams here? Okay. So, this, what does this code do? Okay, let's look at here what we have. We have a radius of the blade 0.8 meter. Just a number. You can calculate it. First of all, you have to calculate this radius. Okay, from the power given 5 kilowatt, 2 kilowatt, 1 kilowatt, whatever, and the velocity given, you calculate the radius. Okay, so you put the radius here, density of water, and the water velocity. So your power is 746, Cp value is 0.4. This one, TP speed ratio is important parameter, then you have to decide. And also number of blade you use, 3 or 4, you have to decide. And alpha angle of attack. This is the most important parameter for aerofoil. What type of aerofoil we are using? We are using aerofoil type here. Aerofoil type SB22. SB22, and this has got coordinate direction between X, C and YC. Okay, so these are the parameters for aerofoil locations, and then you have to scale it up and things like that, and then you plot it. Okay, so these are the simple equations you put it into this code. So first one you are looking at is the radius versus chord length, and you can see if your radius increases, chord length is set to drop. As you said before, at the smaller radius you have a longer blade, then blade is squeezed and become small. Okay, then we look at the twist angle, how much you progress from the hub or from the center line. When you go away, how much blade you have to twist to get the optimum. And in the beginning, twist angle is 35. So first blade has to be twisted quite a lot, and then if you go down the front edge, only 5 degree, not a lot. And if you have to plot that, all the blade at different section, so first blade has got 35 degree twist. That's why it's on this slide. The next blade, which is away from the hub, has got this chord length and different twist angle. And the final one has 5 degree twist angle here. So this is a 2D curve of the arrow profile with a twist along the length of the blade. Okay, and if you want to plot it, combine it together in a 3D plot, this is your actual blade profile. So first one has got quite a large twist, and then you can download this data point, and then you can put it in solid words, and then a function called loft that can allow you to add those sections into a solid blade. Okay, one blade. Then you can copy it into 3 blade, and then you can do CFD simulation and things like that. Tomorrow, I think we have a whole day of CFD simulation exercise and talk. You understand? So that's how you design a blade. So coming back to 5 kilowatt, I could have put 5 kilowatt here, right? I didn't put it because I will give you the code. You put it 5 kilowatt here. You put your radius, you have to calculate the radius, and your velocity is 2 meters per second. So none of the number I actually give you to your actual design code. So if you get access of this, speaking with Professor Sibayan, then you can play with your this If you don't have Spider, it's a Google Colab. You just put it. You don't need to understand. You put it, run it. It's very simple code. If you read it, you can understand. Okay. So that's will help you to design the code. Quite a number of code I have written for your calculation and things like that. Okay. And these are the control. Control we will teach it later. Is that clear? Is that clear what I am saying?
Yes.
Okay, so the code is there. Will be shared with you, so you can play with it, design it, and things like that. Now I go back to my slide. Where is my slide here? Up to this point. Oh no. Yeah, it's here in that this slide. So, okay, give me a second.
Sir, if possible, please share PPT also.
Second.
If possible, sir, please share PPT as well.
Huh?
Sir, if possible, please share PPT as well, sir, after each and every classes, after the individual classes.
Oh, slide.
Yes.
Oh yeah, of course. You will be given all sorts of slide. Yeah. So coming back to my original slide. Yep. So that's. I think I have a Excel code also in the folder that does the same thing. Okay, but this give you graphical presentation and things like that. So again, your exercise, you use this code to go back to design your. This is 5. What's the exercise they give you? 5 kilowatt. So 5 kilowatt, 2 meter per second, and yeah, I give you a lot of ideas, lot of parameters how to calculate, design code written in Python. So you should be able to come up with some initial engineering design. Now, as long as on top of that, if you can learn about triangle, velocity triangle, angle calculation, use those formula, then it will be a worthwhile exercise. Yeah. Now in the afternoon we look at materials for this type of blade. Yeah, what type of sustainable material you can use for blade design. So before I leave, I can ask another question. Can anybody tell me up to this type what type of blade design or what type of blade design you are thinking for your exercise? I will check tomorrow with all your note and a sketch whether you have done horizontal, vertical, whatever type of design. Okay, so I give you some clue here, some exercise, some note, but I also want you to think innovatively and come up with a design, mooring system and cabling system and materials. So before I leave, can I ask you one or two very quickly, what type of material you will be using for a hydrokinetic turbine blade? Anybody?
Carbon fiber.
Carbon fiber. Why?
Because the properties is important, your resistance will be not.
Okay. Carbon fiber lightweight,
Yeah,
maybe
lightweight and
last a long time.
corrosive.
Is it easy? Manufacturability is easy.
No, sir.
Folding, molding, not easy. That's the problem. You say something?
Anodized aluminum. Anodized aluminum.
Anode.
Because we are talking about the hydrokinetic turbine. So turbine blades all are almost placed under the water.
Yeah.
So in spite of we take consideration.
Anyone else? Any other material? No. No copper. We said no copper. Why?
It's a heavyweight material, sir.
Okay. Silver? Okay. No. Okay. What else? Huh? Polymer. Yes. Good. Polymer. Yeah. Polymer can be used. Yes. Last one. I want to take last one. Wood. Why not? Wood. No. Okay. You are saying no wood. What do you think in the front? Wood? Wood is available? Readily available wood?
Yes.
Yes,
Is it readily available here?
yes.
What is wood used for? Burning, cooking, or some other? What is the high value of wood? High value what? Furniture, right? So if I think you can create a business of wood also in turbine. If the price is low, I don't know the price of wood, but if it is cheaper than aluminium, you say, and you can treat the wood, right? You have to treat the wood so it doesn't soak up water and things like that. But wood could be a interesting material to use for turbine blade, because then you can have a local maybe industry using the skill set that already exists in wood carving, wood making, boat. I talked about the boat, right? Those who are working in the remote area making boat, they may be using wood to make turbine blade also. Yeah, it may not last long, but that's also very good. So you change it. So you keep a permanent business, right? After 2 years you change the blade. After 2 years you change the blade. What about that? Yeah? Okay, so think about those are the no ready-made book answer. I am not interested to learn about what is written in the book. I want to know what is your personal experience working with metal, working with material. Somebody says heavy, already said. Yeah, that's a good answer because which is your experience from other sources, right? It's not necessarily you find the answer in the book. Okay, so thank you very much for your attention. We have a long 3-hour session today, so we have a lunch break now, and then we pick up in the afternoon. Next session is at 3. Did you find this session valuable? Anything you learned new? Yeah, useful, anything? Okay, good. Okay, so I will catch up with you later in the afternoon. Yeah. Thank you.